Next example we're going to take a look at is going to be the following. A ball is launched from the ground at an angle of 53 degrees above the horizontal. It lands a total of 200 feet away. What was its initial speed? Now, we went through the process of actually deriving where the position function comes from, but what I'd like to do is go ahead and start with the acceleration function and start working our way backwards. Now, for the acceleration in this case, we were told that this is 200 feet away. Now, given that it's 200 feet away, what I'd like to do is use the acceleration due to gravity that has units of feet per second per second. So, 32 feet per second is the acceleration due to gravity. Taking an antiderivative and plugging in our initial condition, this will be the horizontal component of the velocity is going to be whatever the initial speed is, times the cosine of 53 degrees. We'll do the same thing for the acceleration. This will be negative 32t plus whatever the initial speed is, times the sine of 53 degrees. Now, it does say that the ball was launched from the ground, so the initial position of the ball you may assume to be 0, 0. So when we take another antiderivative, we will get initial speed times the cosine of 53 degrees times t, comma, negative 16t squared plus initial speed times the sine of 53 degrees times t. Now this would be the position of the ball after t seconds. Now the other thing that you could do is break this down into components and say here's your horizontal component and here's your vertical component, and we can go from there. The additional piece of information that's given to us is the following. It lands 200 feet away. It lands 200 feet away can be interpreted as the following. When y is equal to 0, x is equal to 200. Now, once you plug in x equals 200 and y equals 0, then this is going to turn into a system of two equations, and coincidentally, we have two variables, the initial speed as well as time. If we can eliminate the time variable, we should be able to solve for the initial speed. So setting y equal to 0, we're going to get 0 is equal to negative 16 t squared plus initial speed times the sine of 53 degrees times t, and for the horizontal component, 200 is equal to initial speed times the cosine of 53 degrees times t. Now you do have two options here. We do need to eliminate the t variable so that we can solve for the v0 or initial speed variable. So in one of these two equations, you're going to have to solve for t. Now, strange as it might seem, I'm actually going to recommend that you solve for t in the first equation. Reason being, you already have this thing in a form where we can factor out a greatest common factor, interpret it, and set it equal to 0. So this lets us know that either t or negative 16t plus initial speed times the sine of 53 degrees is equal to 0. Now we can interpret t equals 0 as when the ball is initially launched rather than when it's landing. So we need this thing to be equal to 0. Solving that thing being equal to 0, we can do so by subtracting the initial speed times the sine of 53 degrees over to the other side and then dividing by 16, or negative 16 as the case may be. So this is the time at which the projectile is going to land. What we're going to do is take this and plug it into the x equation so that we can then solve this for the initial speed. So this is going to be 200 is equal to initial speed times the cosine of 53 degrees times this nice expression over here. Initial speed times the sine of 53 degrees all over 16. Now there are several identities that you can make use of at this point, and this also lets you know where one of the formulas from physics comes from, where if you know the range of a projectile, you can calculate its initial speed. Combining all of these things together, we're going to get the following. 200 is equal to the initial speed squared times the sine of 53 degrees times the cosine of 53 degrees divided by 16. It'll be very straightforward algebra to solve for the initial initial speed squared, which is multiply both sides by 16. Multiplying by 16 is going to give us 3,200. And then dividing both sides by the sine of 53 degrees as well as the cosine of 53 degrees. For a final answer for this one, go ahead and take the square root of both sides and interpret this as only the positive square root. So this will be 3,200 divided by the sine of 53 degrees times the cosine of 53 degrees. Now, as far as I'm concerned, that is a great looking final answer, and any mathematician would be happy to have it. Unfortunately, this is a real world problem, and therefore we should probably give it a real world answer. Which is why I'm going to grab my handy dandy TI-84 plus CE so that we can approximate this answer. Now, I would like to point out that this is in degrees, so we need to make sure that our calculator is in degree mode. Once we verify that the calculator is in degree mode, we can find this expression. So square root of 3,200 divided by, your denominator has multiple factors in it, so be sure to include an extra set of parentheses for said denominator. When all is said and done here, the initial speed of the object in question is 81 we'll round that to the second decimal place and call it 0.60. So 81.60. On problems where you need to round your final answer, I will make it a point to let you know how I would like you to round your final answer so you don't need to worry about things like significant figures. Now do keep in mind though that if this is a rounded answer, you should have units associated with it. Units in this case, we were dealing with a speed. We had feet per second squared earlier, so as a speed this would be feet per second. And that is our final answer.